All right, so today we're going to formalize the idea of using matrix multiplication to accomplish transforming a vector geometrically. In lesson 1.8, we talked about how to prove whether a transformation was linear. And what we talked about was that addition had to be preserved under the transformation, and scalar multiplication had to be preserved under the transformation, and that is what made it a linear transformation. So we're going to continue to underline that idea, and we're going to be discussing all the different matrices that can achieve transformations that can, for example, flip shapes over, rotate shapes, project shapes, and eventually we'll go to actually being able to move shapes, which is more complicated than one would think. So we are going to discuss, as I said, linear transformations that are achieved through matrix multiplication. This particular matrix, matrix A, is defined by multiplying by vector V. And here you can see that matrix transformation. And because this isn't a square matrix, you can then know that it's not keeping within the same dimension. So if it's not a square matrix, you are moving out of the vector space you're in. So this one transforms from R2 to R3. And we know that because this matrix is a 3x2 matrix. So a 3x2 matrix goes from R2 to R3. And so if we look at creating a 3x2 matrix, such as this one, and multiply it by any given vector in R2, such as x, y, we can see where the transformation, as it is listed here, comes from. If we do row by column multiplication, we multiply row by column here, we get y for the first component, and then row by column, and we get negative 2x plus 2y, and then row by column a third time. We can see how we would get x for our last one. So that is how this particular transformation can be defined using a matrix, because you can see that the matrix multiplication works out to be that component by component description. And so it takes something in R2 and maps it to R3. And tomorrow, we're going to talk about different types of linear transformations, ones that are either one-to-one or onto. And just a quick brief description, one-to-one means every vector in one, the pre-image, maps to exactly one vector in the image and vice versa. So it maps one-to-one. So every pre-image maps to exactly one vector in the image space, and every vector in the image space maps exactly to one vector in the pre-image space. That's one-to-one. And then we'll also discuss transformations that are onto. Onto means, for example, if this was onto, I would map to every single vector in R3. So if you map onto a space, it means I go to everywhere in this codomain. So everywhere into R3 do I get to go to. And tomorrow we'll talk about how to prove whether something is one-to-one, meaning one pre-image maps to exactly one image, and onto, meaning I get to go everywhere in R3 space if that's the codomain. All right, so let's take a look at this example. It says, let the transformation T which maps from R2 to R3, be the linear transformation defined by this particular rule, which takes a vector that starts in R2 and goes to R3. And if I'm asked to find that matrix A, all I have to do is then look at the rule for the matrix. So to find A, we know it's going to be a 2 by 3 matrix because it maps from R2 to a 3 by 2 matrix because it maps from R2 to R3. So to find matrix A, I have to consider what is being done to my pre-image to my image. So you can see what happens from x1, x2 to then our vector in R3. And you can kind of identify the columns. And you can see along my x1s, I have one x1 here, 3x1 in my bottom component, and no x1s in my middle component. So that means my x1 is going to be 1, 0, 3 in my matrix A. And then my x2 coefficients are -2, -1, and -5. So that's just going to be echoed in that matrix. So identifying the matrix is just as basic as looking at the coefficients of that x1, x2, x1 and x2 coefficients. And if you want to test it out, you can just take your matrix A, multiply by x1, x2, your pre-image, and see if you get that as your image. And if you do, you know you have identified the correct A as your transformative matrix. Any questions on that? Okay, now let's think a little creatively. If we wanted to write a matrix that took a vector and doubled it for vectors that are going to remain in R2. So you want a vector that starts in R2 and ends in R2, that doubles in size. What do you think the standard matrix A that you multiply by to achieve that transformation, what do you think that matrix would look like?
2, 0, 0, 2.
Okay, let's check out your theory. So if we take a matrix, or a vector, AB, you would get 2A, 2B. Nice job. How'd you come up with that?
I used the 13.
Good. Yeah, so that would be a dilation matrix because it essentially doubles every component. And you could see if maybe you just would want to, like, how would if we just want to double the X values and not the Y? Okay, let's check that out. So if you want to double just the X component, let's multiply that times AB. I would get 2A and B. Nice. All right. And now we're going to kind of formalize this process so we can figure out how to do even more complicated things besides just doubling. And the way we do that is we kind of pick apart the identity matrix. So when we first learn about vectors in Algebra 2, we learn about the identity matrix, which is 1, 0, 0, 1 if we're in R2. If we're in R3, it's 1, 0, 0, 0, 1, 0, 0, 0, 1. And it's made up of the vectors I and j, or in 3D, I, j, and k. Now, when we're talking about matrix transformations, they call those vectors E1 and E2. I believe they're called like the elementary vectors for E1 and E2. And so the identity matrix in R2 is made up of E1, which is your first column vector, and E2, which is your second column vector. So if you want to mess with the x component, if you want to transform the x component, you transform E1. If you want to transform the y component, you transform E2. And so the way you think of writing a transformation is you think of, well, what do I want to happen to the x in my image? And what do I want to happen to the y in my image? And whatever you want to happen to the x, you modify E1. Whatever you want to happen to the y, you modify E2 because they represent movement in the x versus movement in the y. And so that's how you build a transformation matrix, is just starting with I in any dimension and then modifying E1, E2, and E3, E4, depending on how many dimensions you're in. All right, so let's do it. Let's find the linear transformation, which transforms within R2. So we're talking just our normal flat two-dimensional plane that rotates each of the vectors E1 and E2 counterclockwise, so a positive 90 degrees. And then explain why all vectors in R2, why it rotates all vectors in R2 counterclockwise 90 degrees. So the way I'm going to think of this is by drawing a little picture. And then I'm going to picture what happens when I rotate E1 90 degrees clockwise. So E1 becomes what when you rotate it 90 degrees clockwise? What would be the new vector when it's rotated 90?
0, 1.
Yes. So E1 becomes 0, 1 under the 90-degree rotation. And then E2 which starts up here at 0, 1, becomes what when you rotate it 90 degrees? Yep, negative 1, 0. Perfect. So it becomes negative 1, 0. So my pre-image is just my identity matrix. 1, 0, 0, 1 goes to 0, 1. That's my new E1. Negative 1, 0. So I think of what happens to E1. E1 becomes 0, 1. E2 becomes negative 1, 0. And that is the A for a 90-degree rotation. And what we can do to kind of explain why T rotates all vectors in R2 counterclockwise 90 degrees is we can say, in general, if I take this vector A, 0, negative 1, 1, 0, times a standard vector xy, what I'm going to get is negative y x. 0, negative y, and then x. And let's just look at how that appears on a graph. Let's say this is the vector x, y, and then if I consider negative yx, negative yx, what's the relationship between the slopes of those two vectors? Yeah, the slopes are opposite reciprocals, therefore the vectors must be perpendicular. So you've kind of shown that that relationship must be perpendicular, it must be a 90-degree rotation there. So we can develop this idea for every single rotation, reflection, everything. And that would take a while because we'd have to look at everything. There's a lot of things we can do geometrically. So instead of doing that, I'm going to take you through the matrices for a bunch of common transformations, but know that you can go through this process for everyone. You start with E1 and find out what happens to the E1. You then go to E2, find out what happens to E2, and then you just rewrite the matrix given the transformation of E1 and E2. So our first one is reflections. And so these are reflections in the x1, x2, and over the line x2 equals x1 axis. Is this too small for you? Because I can zoom in and then scroll. So the x1 axis is the horizontal axis. That's what we know as the x-axis. So you can see if you're reflecting something in the x-axis, you make the y negative. So the standard matrix A for doing that is just you make the y value negative. And that's reflected right there. Reflecting in the x2 axis, you flip over the y-axis, and there you make the x negative. So that's shown right there. The E1 becomes negative 1, 0. In other words, the x value is made negative. So a lot of these, I know it might be overwhelming to not have a note card for this particular test, but it's kind of, if you think about what's happening, you're reflecting over the y, so therefore the x is negative. The x is negative, E1 becomes negative 1, 0. Reflecting through the line x2 equals x1, that means essentially x and y, that's the line y equals x, the x and y values are switched. So you can see in the A, you switched E1 and E2. So those are just interchanged. E1 and E2 are switched. So if you had the vector 4, 3, it becomes the vector 3, 4. And that's what happens when you reflect across the line y equals x, or in other words, E1 equals, or x2 equals x1. And those are our typical reflections. Questions on those? two more. One is the line y equals negative x, or in other words, x2 equals negative x1. It's a similar A matrix, but both are negative because you're not only flipping the x and the y components, you're also changing the sign of the x and the y components, and you're flipping it over the line y equals negative x, or in other words, x2 equals negative x1. And this particular matrix is the same one we were describing in number 13, which I think we've talked now 3 ways we could describe it. We could say that we are flipping it across the x, across the y. We could say we're reflecting it through the origin, or we could call it a 180-degree rotation. And it all accomplishes essentially making the x and the y values negative. And so you can see E1 and E2 stay in the same spot, but they become negative. Next, we have making things bigger or smaller. And we talked about how to do that a little bit. So we can contract or expand along the x or along the y. If your value is greater than 1, it's going to make it bigger. We're talking between above 0, though, because if we make it less than 0, you're going to be starting to flip it. If it's greater than 1, it's going to make it larger. Between 0 and 1, it's going to make it smaller. It'll be a contraction. And we can contract along the x or along the y. Along the x, you'll be modifying E1. Along the y, you'll be modifying E2. And so these are some of the ways we can scale our vectors or our shapes. And we can also do both at the same time, like we did in that example where we were scaling both the x and the y by just combining these into one matrix. And we've already talked about shears. We did that in our last lesson, but this kind of gives us a more formal description of the different shears. So we can shear horizontally or vertically, meaning you can take a shape and start moving one of the sides, a quadrilateral, start moving one of the sides and making it more parallelogram-esque. And you can shear something horizontally or vertically, depending on how you'd like to move one of your sides, and it will involve you switching. If you are moving it horizontally, you're going to be modifying E2, and if you have a vertical, you're actually modifying E1, so a little bit different. And we know when we shear, we do preserve the area. We're starting with a rectangle. And depending on if K is positive or negative, it will show you kind of the direction of the shear, whether you're sliding that side up or down. Now, unfortunately, today we are not going to be covering translations. We're not going to be able to move our shapes yet. The reason for that is you actually have to take the shape out of the dimension to move it. So you're not allowed to like drag the shape along 2D. You actually have to move it into 3D in order to move it. So that requires a new chapter before we learn how to do that. So we'll do translating, but not yet. Lastly, we're going to talk about projecting. So recall projecting is when you have, let's say, a vector, and you're going to, let's say this is our vector, and you shine a light on it from above. So here's your light source, the sun. You shine a light on it, and it's the shadow. And it's the shadow either on the x-axis or the y-axis if we're doing a projection in R2. And so the projection takes a vector and just kind of smushes it onto an axis, and it can be the x-axis or x1, x2. It can be onto a line like x1 equals x2, and it basically kind of obliterates one of the coordinates. So if you're projecting onto x1, it makes the x2 coordinate 0, and if you're projecting onto the x2 axis, it makes the x1 coordinates 0. So it's all about like smushing it up against the axis. And those are vector projections. We learned about them in chapter 9 of Calc 3. But vector-wise, it's really easy because you just zero out one of the components. Questions on that? And lastly, we have the very exciting rotation. So you're also able to rotate a vector. And this refers to counterclockwise rotation. Which is our positive theta. This one is not, I don't think, in your textbook, or it's not easily found in your textbook. I think it was buried in a problem or somewhere, so be sure you have it somewhere in your notes. You're able to study it. So this achieves a rotation in the x1, x2. If you're doing this in 3D, it's a whole different equation because you need more components. The A is bigger. And you just plug in the angle, and that will tell you what your matrix is. What rotation is happening there? How many degrees is that one? Or radians?
90 degrees. 40.
Yeah, and it's actually a little harder to tell here. I just go vertex. Like here's the lower left to kind of, or is it going to here? Yep. So I think we're at our 4. So if we were to find the rotation matrix, I think it's radical 2 over 2, negative radical 2 over 2. That would be your rotation matrix for that. And we could also check if we did the rotation for the 90 correct. We could plug in pi halves to that one. Questions on that?
If you want to do it other way, would you just...
You'd plug in negative pi over 4.
Oh, yeah.
Yeah, so you want to rotate in the or the negative, the clockwise rotation. All right, there's your homework for tonight.